Okay, so I'm trying to bundle a whole bunch of these guys together because they're very similar. Now let me start with this one. Okay, on a truncated tetrahedron, two of which are shown below, calculate the Euler characteristic, and we just calculate this. Okay, V is vertices, so we can just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 of them. And then the edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there's 18 of them. And faces. So now that we've scribbled all over this, it's kind of hard to see. I'm going to erase this so you can see the faces. Again, we have faces. The one on the back, 1. The one up here, 2, 3, 4. And then there's this one, 5, 6, 7. And then the one in the front, 8. So there's 8 of them. And blobs means 3D volume, so there's one of those. So all you have to do is 12 minus 18 plus 8 minus 1. So 12 plus 8 is 20. Negative 18 minus 1, and that's negative 19. And you just get 1. So chi equals 1. That's it. Okay, question on page 5. This is a very similar question. It says, for any polygon which is topologically equivalent to a sphere, regardless of whether it is regular or convex or anything, the angle deficit is always 720. What does the one angle deficit say here? Well, we have two squares, is 90 degrees each, and two triangles is 60 degrees each. Gives you 300 degrees, and if what's the angle deficit? It's how much it differs from 360, so it's 60 degrees. Great. Now, calculate the number of vertices in the cube octahedron. Well, you can just count this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It should be 12, and it will be. But it didn't say count, it said calculate. So let's calculate. To calculate, you say 720 divided by 60. Pull out your calculator, and sure enough, you get 12. All right, calculate the number of squares there should be. Well, there are 12 vertices times 2 square corners per vertex is equal to 24 square corners. But if there's 24 square corners, then there must be 6 squares. Because 24 divided by 4 equals 6. And why 4? Because there are 4 corners in a square. And let's look up above. In this case, it's been given to us. We can see there are 4 around the middle, and 1 on top and 1 on bottom, so that's 6 squares. Okay, great. And how many triangles are there? Well, 12 vertices times 2 square corners per vertex equals 24. I meant to say triangle here. Triangle corners. So 24 triangle corners, but 24 divided by 3 is 8 triangles. Now let's see if there's 8 triangles up above. Yep, there's 8 triangles, so we're good. Are there any more questions? Make sure that if it says calculate, you calculate, and you don't just count, because that's a common student problem. Okay, question 6. The diagram below shows a pattern for a truncated icosahedron. Yay. And it says exactly the same thing as the last question, which says, okay, what for any polyhedron, blah, 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 blah. Yep, 720, angle deficit. What is the angle deficit at one vertex of a soccer ball? Well, there's a 108 here, a 120, and a 120. So you add these guys up. Okay, So what's 360 minus 348 is 12. And that's the angle deficit at one vertex. And then you go 720 over 12, because 720 is that magic number that everything always adds up to, which gives us 60 vertices. All right, calculate the total number of pentagons while we look. See, I want you to imagine taking a pair of scissors, all right, and cutting this little circle out at every single vertex on the entire ball. And in which case you'd have all these little pieces. You'd have a little piece that looks like this, that's black, and a little piece that looks like this, that's white, and another little piece that looks like that, that's white. They all look pretty much the same. And these little tiny pieces. So you'd have a whole bunch of these floating around. If you have 60 vertices times 1, because one pentagon per vertex is equal to 60 pentagon corners. Then you put them in piles of 5, and that represents the fact that you have how many? 12 pentagons. See, pretty easy. Now, how many hexagons? Well, it's almost the same, but since there are 2 hexagons per vertex, you need 120 hexagon corners. And then 120 divided by 6, why? Hex means 6, 20 hexagons. Now, unlike in the other problem, I didn't give you a picture of it, so you can't just count them up to figure out if you're right. And you're right, because I'm telling you you're right, but that's fine. All right. Next is cube octahedron. Euler characteristic here. I feel like I did this one before, but last time we did a truncated tetrahedron. All right, so let's go ahead and figure out the Euler characteristic. Vertices 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then what do we do for edges? This one is just as easy as they come, because you're just being asked to count how many edges and stuff. There's 4, there's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24. 24 edges. And, okay, what a mess. How many faces? Okay, 4 triangles on the top, 4 more triangles, so 8 triangles. And we have 6 plus 8, so we get 14 faces and 1 blob. So 12 minus 24 is negative 12. 14 minus 1 is 13, and you get chi equals 1. All right, that was easy. Question number 9 is, oh, we actually just did this one. It's a dupe. Okay, and number 11. Okay, now find the internal degrees in each angle of a regular polygon having 10 sides of equal length, yada, yada, yada. So you pull this formula off your formula sheet, and the n is 10, 8 times 180 over 10, and you calculate it, and that's going to be 1440 over 10 is equal to 144 degrees. Now let's actually read the question. Find the internal degrees of each angle in a regular polygon. Yep, that's right. Also find the sum of the internal angles, 720, right? Oops, no, I'm wrong. Sorry, that's not what I meant to say. Wrong question. I am thinking of the other question, and you knew that. Okay, the sum we were looking for is up here, right? So 1440 is equal to total of all internal angles, and this is one internal angle. And that's enough for this video.